screen. Okay, great. So the screen is yours.
Great. So good afternoon. I will follow up on Remco's talk, and I will be talking about microwave links in the context of urban stormwater management. I guess that our German colleagues invited us because we work at a smaller scale than most of the previous speakers, and also because we collaborate together for some time, and now we even run together projects where we try to join data from microwave links from Germany and Czech Republic to create like transboundary rainfall maps and improve microwave link rainfall estimates. But back to this urban drainage and stormwater management. Urban drainage systems are hidden underground and thus not usually attract public attention. The exemptions are complete failures of this system during extreme events, and then we hear about them also in global media, and we hear about them also from time to time during less extreme but still heavy rainfalls due to accidents or some environmental or health problems related to local system failures. But rainfall affects drainage system also during light rainfalls, and operational rainfall observations are crucial actually to optimally operate wastewater treatment plant and control structures in drainage systems to reduce pollution and health risks, optimize operation costs, harvest rainwater and other tasks. The optimal operation strategies can be, however, quite different when we come to more heavier rainfalls with written periods 2 or 5 years. And here the drainage systems their capacity is often exhausted, and we need to have some nowcast or rainfall forecast to prepare the system for these heavy rainfalls, for example, to empty retention tanks. And many cities are now also redesigning their drainage system to increase the retention capacity and build structures like huge retention tanks, which can be seen on a figure on the right. And for such structures, we also need some like reliable historical data for design rains, because such structures are really expensive. And when it comes to extreme events, we can do very little with drainage systems, but we need early flood warning to mitigate the damages and danger of life. And we also need some like good historical rainfalls and climate projections to prepare our cities for these extreme events and redesign them to make them more like flood resilient. Urban catchments are characterized by are usually much smaller than river catchments, and they are characterized by a large ratio of impervious surfaces on which runoff is generated extremely fast. And therefore, when we want to operate drainage systems, we need rainfall data with high spatial resolution and with high temporal resolution, usually like minute resolution and spatial resolution 1 square kilometer. So for this purpose, ground rain gauge observations are insufficient. So meteor radars are increasingly used in urban drainage operation. The countrywide products for meteor services have usually not sufficient temporal resolution, and these radars measure quite far over the ground. So there are also like increasingly local body radars installed, but these are often like cheaper devices and affected by many errors. So microwave links might be like an appealing source of additional rainfall information for urban drainage modeling, because they provide close to ground QPEs, and this rainfall information is path integrated, and the lengths of microwave links are often in a similar scale as urban catchments. Another nice or appealing thing is that microwave link networks are densest in populated areas. You can see here a map of France with number of microwave links per 4 times 4 square kilometers, and you can clearly see the biggest cities, Paris and Lyon, and a highway between them. And you can also see that there is not so many microwave links in Alp regions where there are less people living. And another important feature is that we can obtain microwave link data with minimal delay and with very high temporal resolution. Basically, with simple management protocol, we can poll the microwave links at 10-second temporal resolution. And next slides, I will try to give some answers on how we could use microwave link observations to improve urban rainfall runoff modeling, and also how to make this data accessible and useful for urban water utilities. We are investigating potential of commercial microwave links for urban drainage modeling at our experimental catchment in Prague. It's like residential area. It's quite small catchment, only 1.3 square kilometers, and there is quite a high ratio of impervious surfaces. There are 19 microwave links there, and we have installed their in-situ flow meter to observe discharge from the catchment, the outlet from the catchment, and also like they are close by city rain gauges used for operation of drainage system, and we installed additional 5 rain gauges to the catchment. So we have quite dense observation network there to test different scenarios. And we have set up rainfall runoff model, distributed rainfall runoff model. So we can basically compare the observed flow with flow simulated from different sources of rainfall data and evaluate this. This hydrograph shows an example where we were comparing simulation of runoff from microwave links. Those are these like blue lines are simulations from single microwave links, and we were comparing it to observe runoff. It's the black line with 95% confidence bounds, which are like measurement errors. And you can see there also like simulation based on city rain gauges, the green line, and also like simulation based on adjusted microwave links. And what we can see that this unadjusted microwave links describe pretty well the runoff dynamics, but they can be highly biased. And adjusted microwave links perform quite similar to rain gauges used for the adjustment. So we were not able to really like come up with some really additional value to rain gauges when we were adjusting. To have like better view how good are microwave links, we did this comparison for relevant rainfall events over three years, and these were like 23 events, and for each of the events, we quantified the difference between the simulated volumes from microwave links and between the observed volumes, and also the Pearson correlation coefficient. And when we look at the results here for all the 53 events, each box plot here represents one microwave link, and we can see that and the links are sorted by their lengths. So on the left you see the shortest links, on the right the longest links, and these shortest links are quite highly biased, but they have usually the links between 1 and 1.5 kilometers have the highest Pearson correlation coefficient to these observed runoff. And when we look on the heavy rainfall, this is even more pronounced, that shorter links are more biased, but the Pearson correlations is really high. So they really capture really well the runoff dynamics, actually much better than the city rain gauges. And what's interesting, when we take all the links and average them, we get really like robust runoff simulations, especially in terms of Pearson correlation. So these short microwave links, which correspond to catchment scale, capture very well the runoff dynamics, but they are sensitive to systematic errors, especially to antenna attenuation. I'll be talking about it later. And this microwave link adjustment, which we introduced to reduce the bias, actually quite a lot destroyed the ability of microwave links to capture this runoff dynamics. So we decided to go or find different ways how to correct microwave links for this bias, and especially for wet antenna attenuation. And we started to evaluate different wet antenna attenuation model. Wet antenna attenuation is additional attenuation which is caused by wetting of antenna radomes. So it's not like caused by raindrops along the link path, but it's something we need to get rid of to get reliable rainfall estimates. And we compared different models, and we were trying to calibrate them using only data from existing permanent networks and look at our results if we can obtain with microwave links better results than when we use the existing networks alone. And first results here are very, very promising. We can see that we can calibrate these wet antenna models even with hourly rain gauge data, which are completely like insufficient to model the runoff dynamics at our catchment. And with this corrected data, we get really, really good results. And these results are good basically for all or for most of the events. So this is promising. And these results are actually comparably good when we model the runoff with the rain gauges which are inside the catchment. And now I will ask my colleague Wojciech to tell you something about our system, real-time system used for operational monitoring with microwave links at city scale.
So good afternoon, everybody. My name is Wojciech Bareš, and I would like to just quickly present the operational product we work on. We call the project Tel for Rain, and the goal of the project is to create a real-time gridded microwave link product at 1 minute time resolution. And on that project, we cooperate with the T-Mobile and the Prague Water Utility and Prague City. So here we work in the domain 60 to 60 kilometers in Prague, wider Prague region, where we employed 800 microwave links and also 23 municipal rain gauges. And we, let's say, received the microwave link data with a 1 minute resolution, and we would like to provide QPEs based on the microwave link observation with a delay of 1 minute. So the system is based on the data collector, which is in the backhaul network of the T-Mobile. And we transfer this data using the interface to our servers at the CTU. And then we process the data and we try to publish using interactive web client to the municipality. So at the moment, this part is operational. The second part is also operational. During this year, we are working on the connector from the T-Mobile network to our servers online. So at the moment, we can just present the tool offline. So we are using offline data. So I would like to try to present here the offline data, how it looks like. Here we can see the microwave link network we monitored in the year 2014. So we work with the data sets from 2014, and we monitor in that time 150 microwave links out of approximately 1,000 of devices in that period. First, what we can display here is a radio signal. So when we look at it, this, for example, this microwave. Sorry. It's sensitive mouse here. So we can display receive and transmitted signal in the time. And from that, we calculate the rainfall rate. So here we can see this is 1 month's data of rainfall intensity calculated based on transmitted and received signals at this microwave link. When we go, for example, to this event, this is event from 20th of September 2014. We see 1 minute pass in average rainfall intensity along this link. From the pass integrated rainfall intensity, we create rainfall maps. So when we click on this time instant, we see the rainfall map for this time instant. So probably we should see some maximum on this link here. And we also can, let's say, somehow visualize the rainfall which is going from the west to the east, which is the common direction of the advection in Prague region. So here we move to this link and we see the 1 minute rainfall intensity on the other link. This is interesting, but of course for the municipality and the water utility, most interesting information are, let's say, area rainfalls over the catchments of the drainage system. So there is another layer in the system which is focused on the catchments of the sewer system. And here, when clicking on each catchment, we can visualize the area rainfalls over the catchments in the time. And as a final tool, what we developed for the city are, let's say, virtual rain gauges. So here I can select the virtual rain gauges, which is 3 to 3 kilometers. And again, clicking on some coordinates, I can visualize, let's say, the area rainfall intensity over 9 square kilometers for that given rainfall event. So this is what we are working now as a operational product, and we would like to connect to the internet or online during this and next year. So at the end, we have to also point out some challenges. There are challenges related to network development. One challenge is business related. So here we can see the network of T-Mobile from eastern part region of Czech Republic, and we see very dense network. These are data from 2015 to 2016, and this is the situation in the year 2017 and 18. So this is related to the network operation outsourcing in between different T-Mobile operators. So sharing of the network between, for example, T-Mobile, O2, and Vodafone in this region. Second, there are technology-related challenges. This is the map of the E-bands microwave links working on 80 gigahertz frequency in 2017, approximately 300 microwave links within Czech Republic. And this is the situation April 2019. So there is approximately 1,000 of E-bands. Today it's even more. And what is the challenge here? This is also mentioned by Remco. So this is the relation between the specific attenuation and the rainfall intensity for K-band microwave links. Here, this is the picture for 38 gigahertz, and we see almost linear relationship and, let's say, low sensitivity to DSD. On the other side here, on 83 gigahertz, we see very high sensitivity to light rainfalls here, but on the other side, high sensitivity to drop size distribution. So this is situation similar to weather radars. And what to conclude from our findings and work up to date, let's say we see that the microwave link QPEs can capture very well temporal dynamics and are more reliable during heavy rainfalls. What is known at the moment that we require wet antenna attenuation correction to simulate reliable volumes of the rainfall. About the wet antenna, we found that it can be calibrated with existing range networks in the cities, but the question is how to select appropriate model without, let's say, reference observations. And the final conclusions are related to observation systems. We would like to provide for the region of Prague, let's say, in real time, 1 minute rainfall maps till the end of 2020. And we also would like to integrate with the City GaugeNet data for the wet antenna correction. So that's all from us, and we would like to ask for questions if are. See you.
Thanks, Martin, and thanks, Wojtek. So there is some time for a very short question, if there is one. If not, I only have a very tiny question regarding this outsourcing. So is this, do they have other hardware operators that run the systems, or do you think that it's really the 4 companies that join together and buy fiber optics and or use more fiber optics, or why do you lose certain CMLs from your network?
Actually, microwave links are still there, but they are operated by other operator. So two operators are jointly operating the network. So the data is virtually accessible, but we would have to have collaboration with other operator.
Okay, yeah, that's a difficult thing, yeah, but thanks.
Is there time for another question, Christian?
Yeah, of course, a small one.
Okay, well, thank you very much, Wojtek and Martin, for your excellent presentation. Two short questions for Martin. First question, the rain gauge correction algorithm you use for the wet antenna attenuation, is that applicable in real time? So in other words, do you use rainfall information from, let's say, previous hours? First question. Second question, the hydrological model that you employ with your CML data, does that have any calibration parameters? And if yes, what data source did you use to calibrate those parameters, rain gauges or CML? Thank you.
Yeah, so to the first question, we actually calibrate this wet antenna attenuation model like in advance, and it can be applicable then in real time. We don't know how often it should be recalibrated, but these results were for like calibrating like 1 year before and applied 1 year after. So it works. That's good. And to the model, it was calibrated to rain gauges and flow meter data, and there were 2 other flow meters for this calibration. So I think it's pretty well calibrated model.
You might want to calibrate it to the CML data and then see what happens, because obviously
yes. This
your
probably
results will be
improve the
biased.
results for CMLs.